Hello everyone and welcome to this video where we look at the applications of absolute minimum and maximum problems. So we'll be using our skills with stationary points, local mins, local max, but also then apply them to absolute minimum and maximum problems and applications problems, so worded questions, real life problems, and where we can start to actually use differentiation. As always, though, at sort of year 11 level, these problems are a little bit contrived in that they're made up so they're using mathematics that you're familiar with, or topics or geometry or area that you're familiar with. Just remember always that at year 11, we're looking at the absolute basics of the skills, which is a bit scary. But taking this concept idea of understanding that for any function, if we take the derivative, let it equal to 0, that's when we know the stationary points are. When you start to apply that to much more complex functions, that still holds true, and that allows you to, say, calculate trying to make the rate of closure between a International Space Station and a supply rocket. You want the rate of closure to be 0 when they get next to each other. So that's how you'd be using these in extended real life situations. So yeah, learning intention is to apply maximum minimum skills to real life problems or real life problems. Your success criteria will more deal around with, can you successfully interpret a problem, identify the function in it, identify the derivative that you need to find within it, letting that derivative equal to 0, solving, and then getting the relevant information and then converting it back to the contextual situation. So okay, you have a problem, but then you're dealing with time. You're finding when the gradient is equal to a certain time. You then have to state that time relative to the problem. So it might be, the river height is at a maximum of t equals 8, but it might be t is equal to time after 2 p.m. So you then actually need to convert that to 10 p.m. But let's have a quick go. For a function that has, we're going to first quickly look at absolute maximum and minimum problems, and they occur when we have a function for a defined interval. So if we have a defined interval, we can also say there must be an absolute maximum and minimum, because if we think quickly of just our favorite quadratic, a cubic, if we have something like that, if we start to restrict that down to a domain, let's say if we go between there and there, so we're only dealing with this green section, we can now say, okay, that point there, that is our max, but it's also our absolute maximum, because nowhere on the graph, because of the domain, does the graph get high, because we're not including that, and we're not including down to the left, and we could also say down here is a minimum. Now, as it says here, note, the above are not always stationary points. Absolute maximum point and absolute minimum point might not always be a local max or local min or a turning point, because what could happen, let's say for example, instead I don't do the domain tool there, I change my domain to be somewhere down here. So now my function that I'm counting goes all the way up, all the way down and around. So here we have a local min because there's a turning point there, but as we know, down here is actually the lowest point, so down here is our absolute minimum point, because that's the lowest it gets in our given domain. So the trick with any of these problems, as soon as you see, if we're given a function and it says find the absolute min and max, you want to find if there's stationary points, but you also want to check the endpoints. Okay, so you want to check stationary points, but you also want to check the endpoints. And it also helps if you are recognizing the type of function, because if you can recognize the type of function, you may realize much quicker whether you need to consider the stationary points or consider the endpoints. So for this example, we have f of x is equal to 2 minus 5x, which we could also write as negative 5x plus 2. That's just a linear equation. That's just a straight line, and it has a negative gradient. So even if I get my scale and my intercepts completely off, we know it's a downwards trending line. Okay, and it's a straight line, so it doesn't matter wherever we pick. Okay, if we have a given domain, well, the highest point is going to be at the left and the lowest point is going to be at the right. So for this one, we don't even need to find the derivative. We can just substitute in. So straight away, we let's find the left-hand point, which will actually be our maximum point. So we're going to let x equal to -1. So we get f of -1 is equal to 2 minus -5 by, something's beeping in the background. That 2 by -1, so we get 2 plus 5, we get 7. So our absolute maximum point is at -1, 7. We want to write what it is next to it, so it's our absolute max. And then our minimum, as we said, it's a negative gradient linear function, so it's going down. So the min must be at the furthest right point. So we're going to let x equal to 3. So f of 3 is equal to 2 minus 5 by 3 is equal to 2. Take away 15 gives us -13. So we get 3, -13. And that is our absolute min. That's the lowest point we have, y coordinate wise. And so that's just really quickly to show that it can be an endpoint. A linear function doesn't even have a stationary point. But let's now have a look at this case. Find the absolute minimum and maximum values of the function where f of x is equal to x plus 1 all squared between negative, we had given the domain between -2 and 0. So we have f of x is equal to x plus 1 all squared. I'm going to expand that out just so I can find the derivative. So we get x squared plus 2x plus 1. So it follows on f dash of x is equal to 2x plus 2. We want to find where the turning point is. We know this is a quadratic of some sort. It's positive quadratic, so let f dash of x equal to 0. So we get 2x plus 2 is equal to 0. 2x is equal to -2. X is equal to -1. So our turning point, TP x coordinate is equal to -1. So our TP y coordinate will equal to f of -1. So we're subbing it back into our very original equation. So we get -1 plus 1 all squared gives us 0. So our turning point is at -1, 0. That is inside our domain. That is inside our domain. Since this is a regular quadratic here, let's actually fix the sketch up a little bit. Sketch looks like that. The turning point's there at -1, 0. And we have some domain from -2 to 0. So across like that, across like that. That is clearly the lowest point in our domain, the turning point, and nowhere in the graph, that even if we didn't have a domain, that the graph doesn't get lower than that turning point. So our absolute min is at -1, 0. Now we just need to find our max. Well, our max will be either the left-hand endpoint or the right-hand endpoint. So we just need to substitute those in to find what they are. So f of -2 is equal to -2 plus 1 all squared is equal to -1 squared is equal to 1. F of 0 is equal to 0 plus 1 all squared, which is also equal to 1. So it turns out both the endpoints, it makes sense, the turning point's halfway between our left domain boundary and our right domain boundary. The quadratic is symmetric. So it was, before we even found these 2 points, I knew they were going to be the same height. So it turns out our absolute max is 2 points. It's the left hand side and the right hand side. So we have -2, 1, and we also have 0, 1. That's the highest point in that given domain. So to sum up for those problems, when you're asked to find the absolute min and absolute max, and especially when it says the absolute, you need to think of not only the turning points, but you also need to think of the endpoints. And think of the shape of the graph. Always doing a quick little sketch will really help with these problems. Right, now the meat of this section, solving maximum or minimum problems when we're doing application style questions, worded questions. Here's the following steps that you want to apply. First off, always try and draw a diagram and label it with as few variables as possible, as little variables as possible. And what I mean by that is not leaving things out. Try and use the same letters over and over and over. So we'll come to a problem where we're dealing with perimeter or area. If you can write something in terms of length and then there's another line that's twice as long as length, don't call that C or some other random variable, call it 2L. Okay, so you want to use the same letters where possible over and over and over, because you're going to try and build an equation. And we want to build equations with as little variables as possible, because you haven't been taught how to do multivariable calculus yet, or multivariable differentiation. So we want to break it down to one variable essentially. As it says, if there is more than one variable, find a connection between the variables from the given information. So a lot of the problems deal with a mix between perimeter and area. So you told something about perimeter, you told something about area, and because of the connection between them, you can do a substitution and gets rid of some of your variables. To do these substitutions or recognizing a link, there's a lot of assumed knowledge. There's many ways that you can have it. Pythagoras theorem, dealing with trigonometry, similar triangles. That one actually comes up. That's normally the hardest questions involve some form of similarity or scale factor, and just standard formulas. So what it means by standard formulas: formula for area of a square, area of a rectangle, area of a triangle, area of a rhombus, area of a parallelogram, area of a kite, things like those. So this is going to pull information from a broad set of area. You then need to find an expression for the quantity to be maximized or minimized. Oh, pardon me, sorry. So generally these problems will be, you want to maximize the area, or you want to maximize the perimeter, or you want to maximize the time. So you need to end up, whatever you're trying to maximize or minimize, you want to make an equation for that. So if you want to maximize area, we want to end up with area equals something. If you want to maximize perimeter, you want to end up with an equation for perimeter equals something. If you want to maximize time, you need to have time equals something. If you want to maximize distance, you need x equals something. Whatever you're trying to maximize or minimize, you need that equals everything else. Because then once you have that, you can differentiate it, let the derivative equal 0, and then solve, and that tells you where your local max and local mins are. Reject any unrealistic solutions. You also want to check the nature of the stationary point. So is it a max, is it a min? And then check also, is it absolute? So this was, is it a, sorry, max or min for this point here? And then for this point, you want to check, is it an absolute or is it a local? So you also then need to consider the endpoints. Make a rough sketch of the graph as needed, and then answer the actual question. So there's a whole lot involved in these. So contextually, you need to have a firm grasp on the problem. So let's have a look at an example. and do that process. So a rectangular block has base side lengths x and 3x. The sum of its edges is 20 centimeters. Show that the height of the block is equal to 5 minus 4x. Okay, so the advantage in this is we're already given a diagram, but if you weren't given a diagram, you'd certainly want to label it. So we are told base side lengths of x, so that is x, and then the other one is 3x. So we've written those two sides in terms of x, so we've only got one variable at the moment. This side over here is also 3x, this side over here is x, up here is 3x, up here is 3x, that is x, that is x. So I've tried to label every edge where possible. The sum of its edges is 20 centimeters. Okay, so we also have something that we don't know, show that the height, we have the height there, we have the height there, we have the height there, we have the height there. The sum of all its edges is equal to 20 centimeters. So we know that 20 is equal to all the edges added up. So that edge, that edge, that edge, that edge, like all the edges, all the lengths. And so this is sort of like a three-dimensional perimeter almost. It's perimeter of a three-dimensional, it's edge length of a 3D shape. So how can we write that? Well, 20 is equal to how many h's do we have? Well, we have 4 sides that have a length h. We have plus 4 sides that have a length x. So 1, 2, 3, 4. And then we also have 4 sides that have a length 3x, or 3x. Now all we need to really rearrange it is show that the height of the block is equal to 5 minus 4x. So we're going to rearrange this to get h by itself. So 20 is equal to 4h plus 4x plus 12x. 20 is equal to 4h plus 16x. Come over here. Let's take out the common factor of 4. So we get 20 is equal to 4h minus 4x. So we get 5 is equal to h minus 4x. So we get h is equal to 5. So that's a plus, sorry, plus. So we end up getting 5 minus 4x. Done. Okay. Show that the volume of the block is given by v of x is equal to 15x squared minus 12x cubed. So no volume for a rectangular box is equal to length times width times height. And we're just going to do a substitution. So our length is 3x times by our width is x times by our height. We just showed that it is equal to 5 minus 4x. So we get 5 minus 4x. And then we're just going to simplify that problem. Now, a key thing to note, whenever we have these show that problems, we're giving you the answer. You can't start with the answer and work backwards in these show that problems. So it's a bit different to specialist. We want you to start with fundamentals, e.g. knowing, okay, I need to add all the lengths to get the total perimeter equals needs to be 20. Same for part B. You need to start with the concept that volume equals length times width times height. You can't start your show that problem with this bit of information and then work backwards. That's not what happens in methods. The other thing to note from show that problems is you're given the answer, so that allows you, even if you can't do part B, you're given the answer that'll be necessary for the next part. Same in this, we were told that the height of the block is equal to 5 minus 4x. Even if you didn't know how to show that, you could still use it to calculate the volume. So don't give up. As soon as you see a show that problem, even if you don't know how to do that, it's giving you the answer to do the next part. So never give up on the questions after a show that problem. Right, so I was just simplifying this. So we get 3x times x, so we get 3x squared by 5 minus 4x is equal to 15x squared minus 12x cubed as required. So that was just simply knowing the volume of a box's length times width times height. Okay. State a realistic domain for v of x, e.g. allowable values of x. Okay. This takes a bit of intuition. We know x can't be less than 0. Now we can't have a negative distance. So straight off the bat, we know that x must be greater than 0. Okay, and it can't even be equal to 0. We certainly can't have an edge equal to 0. So x must be greater than 0. We also know the height. Okay, the height must be greater than 0, and we also know that 3x must be greater than 0. But 3x greater than 0 tells us nothing new over x must be greater than 0. So we can leave that one out. But all edge lengths must be greater than 0. So height being greater than 0, well, we know from this previous one that height is equal to 5 minus 4x. So we could say 5 minus 4x must be greater than 0, doing a substitution. So we can add the 4x, so we can say 5 must be greater than 4x, so 5 on 4 must be greater than x. So we now have x must be less than 5 on 4. Just by doing that substitution and rearranging, just because of the requirements of the height. So we can now see that x must be greater than 0, what we talked about. I probably should have written these like that. And I'll rewrite this one as well, just for the sake of it. So 0, that was 5 minus 4x, so we get 4x must be less than 5, so we get x must be less than 5 on 4. So we started with x must be greater than 0, but because h must be also greater than 0, x is not allowed to be greater than 5 on 4, because if x was greater than 5 on 4, h would become less than 0. So that's how we actually get the lower was easy, the lower boundary was easy. The upper boundary normally takes a bit of intuition or checking with problems, and it's normally related to do with whatever the fancy substitution you've done at some stage. But there's our domain. Find the coordinates of the stationary point of v of x. Okay, so stationary points, that is when v dash of x is equal to 0. Yes, the derivative is equal to 0 gives us our stationary points. So v of x is equal to 15x squared minus 12x cubed. V of x is equal to 15x squared minus 12x cubed. Did I remember that right? Yes. So it follows on v dash of x is equal to 30x take away 36x squared. We're going to let v dash of x equal to 0. We're letting the gradient equal to 0. We get 0 is equal to 30x minus 36x squared. Take out the common factor. We always want to factorize by taking out the common factor, which is 6. So we get 5x minus 6x squared. Actually, we could take out x as well. Let's do that. So we get 0 is equal to 6x by 5 minus 6x. Okay, so this we could put in brackets like that, and we actually have the null factor law. So we can say it follows on that 6x is equal to 0, or 5 minus 6x needs to be equal to 0. So we get x is equal to 0, or we get negative 6x is equal to negative 5, x is equal to 5 on 6. So the stationary point is either at x equals 0 or x equals 5 on 6. So let x equal 0, we get volume of 0 is equal to, because it's asking for the coordinate, so we need to find the y coordinate or the volume that occurs. X equals 0, so we get 15 by 0 all squared, take away 12 by 0 all cubed, gives us 0, so we get 0, 0 for that one. And then the next one, we let x equal to 5 on 6. And even this is a fraction with squared and cubes, you do need to be able to do this without your calculator. So we get volume of 5 on 6 is equal to 15 by 5 on 6 all squared minus 12 by 5 on 6 all cubed gives us 15 by, right, 5 on 6, that's going to be 25 on 36 minus 12 by 5 times 5 times 5 is 125. 6 times 6 times 6, well, that's 36 by 6. 6 sixes are 36. 6 threes are 9. Plus the 3 is 12. 120. 6 threes are 18. Plus, plus 3 is 21. 216. Okay. Ooh. Ouch. Well, this one isn't nice. We can take out some common factors here. So take out 6 out of that, that gives us 2. Take out 6 out of that, gives us back to 36. So we now need to do, we can do this because we now have common factor. 36 on the base. So 15 times 25. Okay. 5 5s are 25. 5 1s are 5 plus the 2 is 7. 0, 2 5s are 10. 2 1s are 2 plus 1 is 300. We get 375. And then we're doing 2 times 125. That gives us 250. So we end up with 375 on 36. Take away 250 on 36. That leaves us with 125 on 36. So our coordinate for other stationary point is 5 on 6, 125 on 36. Is there any common factor in 125 and 36? 36 is just 6 6s. It's also 3 12s. And 125 will be divided by 3. 120 divided by 3, 12, 3, that is equal to 40. No, because then 5 doesn't divide by the 3, so no. 125 divided by 6. Same thing, because 120 divided by 6 would be 20, leaving the 5. 5 can't be divided by 6. So no, that's as simple as it gets, 125 on 36. So there's the two stationary points. Last bit, state the absolute maximum for your domain in part C, hence find the maximum volume of the block. So this is where doing a sketch comes in handy. So we're trying to find the maximum for your domain in part C, hence find the maximum volume. So we're trying to find the maximum volume, so we want to do a sketch of volume versus x. We know that it is a cubic. Now let's look at it. We were given negative 12x cubed, 15x squared minus 12x cubed. So we had volume equals 15x squared, take away 12x cubed. Write that with the greatest polynomial first, so we get minus 12x cubed plus 15x squared. So it is a negative cubic. And so straight away we know that instead of that, the graph is going to look something like that. And we know it's not a point of inflection because in the previous problem we found out that there was 2 turning points. We found the 2 turning points there. So it's not a point of inflection cubic. So we can fix this sketch a little bit. Actually, I'll leave that one there just roughly, that we know it's a negative cubic. And we know there was one stationary point at 0, 0, and then the one further on was 5 on 6, 125 on 36. Being a cubic means it has to come in like that and down. We then need to consider, and even though this is state the absolute maximum, I'm doing this sketch and trying to do it roughly accurate so that I can draw valid conclusions. We need to then consider the domain. Our domain that we came up with in part C was between 0 and 5 on 4. Okay, so our domain was x needed to be between 0 and 5 on 4. Well, 5 on 6 is 5 on 6 is less than 5 on 4, so that's inside our domain. That's fine. So we have some point over here, okay, at x equals 5 on 4. We don't know what that point is. So we have 5 on 4, comma, question mark, question mark. We don't know what the y coordinate is, but it doesn't matter because the fact that we have this stationary point before it, that's going to be higher, and our question is asking about state the absolute maximum. So the absolute maximum given our domain that we figured out was that x is equal to 5 on 6, y or v is equal to 125 on 36. Therefore, and this is we need to answer the question, that was that very last point, and hence find the maximum volume of the block. So we stated in the sentence, maximum volume is 125 on 36, and we just have to have our units. So our units all the way back at the start was centimeters. So units for volume will be centimeters cubed. And that's the problem done. Now, if it turned out to be the case that our domain wasn't up to x equals 5 on 4 or somewhere else, maybe it was here, where it's less than that turning point, well then of course you're going to have to figure out the end point instead of relying on that second turning point. So yeah, if the domain was restricted and it didn't count that second turning point, then we'd have to figure out that end point right there. But that's not the case. There's a challenge question for you to have a go at. Again, if you can't do part A, that's okay, because it's to show that you're given the equation for the area, you can then use it to do part B. It's the exact same process. You're asked to find when it's the greatest, so you need to consider when the stationary points are or when the derivative is equal to 0, but you also need to take into account maybe some restrictions for the height of the window, as in the turning points might be outside the allowable domain. That's something for you to have a go at yourself. If you have any questions, I look forward to seeing you in class next week, and have a good final couple days of the break.